Alright, so we have this app running, and it looks like this. So this is supposed to be like an autoencoder, and I think I'll talk about the structure of the autoencoder in a minute. But like, these are the so I mean, an autoencoder is you have a set of images as inputs, and it's supposed to output the same images. And so what we're doing here is like our images are these like square images, and we're generating a new batch. Because like it turns out it's pretty easy to synthetically generate images of rectangles. They're rectangles, not squares. And so our autoencoder is let me look at what it actually is, because okay, so the images I believe are like 16 by 16. So let me just draw this. So we have like a 16 that needs to be thicker. Yeah. Okay, so that's like a 16/16 image. And then like 16 squared happens to be 256, just like FYI. And so we reshape it to this 256, and then we do a dense layer with 32 units. So we, I guess, like, yeah, try to compress it down to 32 units. And then, so that's like the latent code, if you will. And then we expand it, also using a dense layer, back to 256. And then we reshape it back to 16/16. So that's what we have going on. And so like, there are weights there's like two sets of weights between these layers, and then between the other layers. We'll call those weight 0, weight 1. And so in the animation, which we're visualizing, I believe, like, so yeah, we might want to call these like the encoder weights, because that's conceptually what's happening, or I mean, like, hopefully conceptually what's happening. So I believe these weights being displayed are the encoder weights. Let me see if I can confirm that, because yeah, this layer is, yeah, because like we're getting L1 weights, and yeah, so L1 weights would be like the incoming weights, so like these are the encoder weights. Okay, so the animation, I mean, like, I mean, it kind of like obviously doesn't work because every time we have a new batch, like we're running the optimizer constantly, so like on every new batch it is optimizing for that batch. So like when the batch is initially presented, it looks like garbage. So you know what would be cool is like if I could turn on or turn off training. So anyway, yeah, like there's I guess kind of the idea for what we were interested in is that if you if the latent code layer, you know, like if it's smaller than like the images, if the autoencoder is going to be successful, then there's kind of an idea of like the weights have to somehow like learn something about the data distribution. And whereas if the latent code is the same dimension, I guess, or larger than the input vectors, then, you know, like it doesn't have to learn anything about the inputs. So, yeah, I mean, I guess like we're vaguely interested in the question of, yeah, like when it is compressing, what is it learning? I mean, but yeah, I mean, I guess we kind of have the problem of this isn't like clearly working presently. Because, I mean, every time we switch a batch, it's, you know, it has to recalibrate for each batch. And these weights look like garbage. And, and then the activations are I believe these are the 32 activations, yeah, of the latent code. And they seem to be like saturating. Yeah, I mean, like one thing that would be good to do would just be to like display the minimum and maximum activations, and also like the min-max values for the weights and like the min-max values for the outputs. the thing with the autoencoder is that it kind of reduces to right, because you can interpret the outbound, like if you fix a unit, you can interpret the outbound weight vector as like a dictionary image. So like in this case, we would have like 32 dictionary images. And then I guess like if you consider the dictionary images or like the dictionary vectors as fixed, then the encoder is like, trying to find, it's effectively solving a system of linear equations, because you have like so we have like dictionary vector 0, which is in our case, like a 256 size vector, and and then you have like a number of those dot dot dot, and like in our case we have up to D32, which would be 31 because of 0 indexing. And so like this is 256, this is 256, and so we're trying to find activations in the latent code. Activation 0, activation 31, such that this linear, like sum, linear combination equals the the target image. And so yeah, like if you interpret the dictionary vectors as fixed, then that's literally, it's not a linear system, because like you're passing this sum, like through a tanh. Oh no, it hit the equal signs. So but anyway, like, okay, so like you can interpret the encoder part as solving, like the encoder is solving this system. But kind of in particular, like it's solving it for, like it only needs to solve it for inputs that are like from the probability distribution, like from the input probability distribution. Because, it says like, over here you have like input 0, and then you have like a lot of these equations, which I think mathematically would be, I think like mathematically or whatever, you could So you're gonna have like the dictionary matrix, which is gonna be like composed column-wise, D0, D31, right? So like these are columns. And so it's going to be like 256 by like number of inputs, which is like, wait, no, that's just fixed. So that's always 256 by 32. And you're then going to have unknowns, which are the activations. And let's see, so those are going to be, yeah, you're going to have this is always going to be 32, and then like you're going to have like a vector of activations for each input. Wow, that completely went off the screen. Yeah, so this is like number of inputs, and so this is like activations, input 0, and then you just have like an arbitrary number of inputs. And so then you're saying you're going to do like the matrix multiplication plus the tanh, and then you need all of that to equal the your training data, which is going to be 256, because like these are images that we've turned into vectors, and number of inputs. And yeah, so that's, so like your unknown, I mean like if you're assuming this is fixed, this is like given or whatever, it's just your image data, and your activations are unknown, and I mean again, like that's almost, I don't, well, I mean like the further kind of like problem I guess is that, by the way, this is like image 0, image in, the problem is that I should call these not inputs but activations. This is like activation for input 1 or input 0, activation for input n. So the problem is that, like, you know, your activation itself, you know, is just given by the first layer, which is literally the encoder weights matrix multiplied by the input for k. I mean, it's like when you're training, I mean, you have control, like, the dictionary vectors are the weights for the decoder. Like, they're just identical to the weights for the decoder. So the like in general, those are under control of gradient descent, and the encoder weights are also under control of gradient descent. So I mean, I guess you I mean, I guess you could. I mean, like, if explicitly my data is being generated by like random linear combinations of these dictionary vectors, right? I mean, that's like what the autoencoder is assuming, right? Because it's saying like I have these. I mean, literally, the output from the autoencoder is a linear combination modulo tan h of a not literally modulo tan, of a of these outbound vectors, right? Like the activation is the weight. So I mean, yeah, I mean, it kind of seems like. I mean, I guess it seems kind of obvious, like if you're generating data using like a dictionary, yeah, I mean, like it. Like if you're generating data using the dictionary with, like k elements, then like the autoencoder should always be able to work. Like, I guess like assuming that gradient descent finds the correct dictionary elements. Because I mean, if you explicitly start with a dictionary and you're like, yeah, I'm going to generate data by just taking random linear combinations of. Although I don't know, I mean, because yeah, but you do the nonlinearity. Well, yeah, I mean, I think that's fine. I mean, like if you explicitly have, the autoencoder and then like you just generate random latent codes, and that's your data. Then yeah, I mean, it seems like it should always work, assuming like gradient descent can like magically recover the dictionary elements. Which it probably can, because I feel like that's convex somehow, but I don't know. But if so like, I guess going back to the actual right? Like we have like this cool animation going, theoretically. So these are the... I mean, I think first of all, I think our images are like too large, but yeah, those are the encoder weights. Well, yeah. I mean, I guess that's what like we could try to do is like generate data using a dictionary and then seeing if like a dictionary of size K, and then it's like an autoencoder with latent dimension of size K should be able to, I guess, like recover like the latent codes exactly. So I mean, we could have like what if your data isn't generated by linear combinations of a dictionary, you know? Is there any data that is not generatable by a dictionary? Actually, it might be cool to rewrite this. Well, yeah, it might be cool to rewrite the visualization this way. It's just that the images are going to be like visualized as one-dimensional vectors. And activations, number of inputs, these would be batches. Yeah, let's like do a thing where we're gonna like revisualize everything like using like matrices as opposed to like sets of squares. I'm also gonna make my images smaller. So yeah, I think that's what we'll do for the rest of this stream, is just visualize, is set up this visualization for the same like training process. Yeah, so I need a new file, and it will be called matrix viz. I think I can kill that one. And so we're just gonna copy paste this over and run matrix viz. Yeah, I'm gonna break the HTML. I don't really know an easy way to fix that, so I'm just gonna copy paste it over. Which is like a terrible way of doing this. Great. Okay, so we're gonna try to visualize. It's also like, yeah, I mean, this doesn't work, right? Like every time you have a new batch, it just looks like garbage. Hold on. Burb.